the next type of isomerism we need to investigate is going to work very similarly to the diastereomers. This is the conformational isomer. And what's going to happen here is because in every alkane that has a single bond, we just have these little sigma bonds. We just have these little single bonds that are free to rotate. And because they're free to rotate, that'll change how the different molecules will line up. Now, molecules aren't just in a stable conformation. They're constantly moving around. They're constantly rotating, spinning, and moving back and forth hundreds of times a second. They're moving extremely fast, and there is a lot of energy being traded around. And so this is something that we do need to investigate. Now, we're going to start by investigating with ethane, which doesn't have that much going on, but it is going to become more important with more, well, we'll say larger molecules. It's going to have a play in this concept called steric hindrance, which will come up more when we start to investigate organic reactions. Steric hindrance is the amount of crowding around a carbon atom. Now in ethane, there's really not much, but ethane is a very simple molecule to start with in order to investigate this. Now what I've got here is the skeletal model and then the Lewis dot structure for ethane. It's just 2 carbons, 6 hydrogens. And then over here I've got this thing called the sawhorse model. Now the sawhorse model is just going to show the position of our hydrogens, and we're going to see that, well, my front hydrogens could rotate a little bit and get lined up. Now let's look at what that looks like on a ball and stick model. I have ethane here, and my ethane on the sawhorse model like this could sit just like so. So I've got all of my hydrogens kind of staggered away from each other. And if I look straight on it, I could see that all of these hydrogens are spaced as far apart as they could possibly be. Now let's draw it from that angle. When we draw it from that angle, what we're drawing is called a Newman projection. So I'm going to draw just like this. And we look at it from the front side. When we do this, it'll allow us to kind of examine where the energy is in this atom. The way I draw a Newman projection is just like this. I've got just a straight triangle, that the point in the middle, this point right here, this is going to be my front carbon. So when I'm looking straight down this ball and stick model, my front carbon is this dot. My back carbon is going to be this larger circle. And so then I've got my hydrogen sticking off the backside. Now, when this shifts, just like this sawhorse model here, when it shifts, it's spinning, it's rotating, and then all of my hydrogens are lined up one in front of the other. So let's draw what that would look like in a Newman projection. So now I've got this. We're just going to draw these a little bit to the side. So I can see my front hydrogens are perfectly lined up with my back hydrogens. Now, that's relevant because each of these hydrogens has its own electron cloud. And these electron clouds are going to resist each other. And so when I'm in this conformation, with all of my hydrogens as far away from each other as can possibly be, I'm going to have the least amount of strain on this molecule. These hydrogens are as far apart as they can be. These hydrogens are going to balance out this hydrogen. So these two balance out this one, so that there's as little strain pulling this molecule apart as possible. But when it rotates into that position, this position where they're lined up, these hydrogens push against each other, trying to break this molecule apart. So there is more energy trying to push it apart. And so we get this energy difference. Now we have specific names for this. When I am as far apart as I can be, we call this a staggered conformation. This is a staggered conformation. When my hydrogens are one in front of the other, we call this an eclipsed an eclipsed conformation. So I've got the staggered conformation and the eclipsed conformation. Now in your workbooks we have a drawing of this that is much better looking than what I've drawn here on the whiteboard. So follow along with that. But what I've got drawn up here is just a quick way to look at these changing energy levels. Now with just a simple molecule like ethane, I only have the two conformations. I only have staggered and eclipsed. As we get to more complicated molecules, we'll have a little bit more diversity. But this serves just to introduce the concept. By looking at the Newman projection, I can see that my first conformation, my angle apart is 0. There is a 0-degree difference between these two, right? There's 0 different degrees between this hydrogen and this hydrogen. There's no difference. When I move into my first staggered position, the first one here, I'm going to have a 60-degree difference. This will be 60 degrees between this carbon, or this hydrogen and this hydrogen, the first two that I was looking at. Now, when I move again, just a little bit more, I get to a 120-degree difference. When that happens, my hydrogens, my initial hydrogens, they're back in line with a different hydrogen. So they're 120 degrees apart from each other, but now they're back in line with another hydrogen. And so I'm going to see this. Every 60 degrees, I'm going to be going through, now here's 180 degrees, I'm going to be going through this energy change. And now the difference in energy here is going to be about 2.5 kilocalories per mole. Calories is just another unit of measurement, just another unit of energy measurement. 2.5 kilocalories would be about 2.5 calories from food, if you can think of that. It's like a single wafer or something. So it's not a lot of energy, but even in small little ethane, this is going to be significant. There's going to be these changes, these measurable changes.